Hi everyone, my name is Ori. Welcome to my talk on subtyping machines. Subtyping is a very important component of object-oriented type systems. Sometimes, though, it can get quite complicated. To get a better understanding of subtyping, we connect it with the well-established theory of tree languages. We do so using a mechanism called the subtyping machine that formalizes computations carried out by subtyping. We address declaration site nominal subtyping with variance. You can find this form of subtyping in your favorite programming languages like C# and Scala. Subtyping is basically a type system decision problem. Given two types, T1 and T2, the type system should decide whether T1 is a subtype of T2. You can find subtyping everywhere in your programs. For example, whenever you assign a value to a variable, or when you invoke a function with parameters. Let us demonstrate. Class B inherits from class A. Therefore, we can assign a B to variable x of type A. This is because a B is an A, or B is subtype of A. We cannot assign a set to x because a set is not an A. What about type parameters? Well, a list of B's is definitely a collection of B's. But is a list of B's also a list of A's? The answer is no, because we should be able to add an A to a list of A's, but we cannot add an A to a list of B's. The opposite is also not true. A list of A's is not a list of B's, because when we read from a list of A's, we get an A, but we expect a B. Let's say that we do want to implement these covariant and contravariant behaviors. For example, if we can only read from the list, then a read-only list of B's is a read-only list of A's, because when we read a B from the list of B's, this B is also an A. To implement this behavior, we declare that the type parameter of the read-only list is covariant, using a special keyword like out in C#. Likewise, a write-only list of A's is a write-only list of B's, because we can write B's to a list of A's. To implement this behavior, we declare that the type parameter of the write-only list is contravariant using the keyword in. This form of subtyping was described in the abstract type system of Kennedy and Pierce. Kennedy and Pierce proved that their type system is undecidable by showing a reduction from subtyping to the post-correspondence problem. Yet they showed fragments of their type system that are decidable. The subtyping semantics in those fragments are restricted in certain ways. So we know that the type system fragments of Kennedy and Pierce are decidable. But now we ask, how complex are they? To answer this question, we draw a connection between subtyping and tree languages. For starters, observe that types are trees and vice versa. This is because polymorphic types are shaped like trees. If so, then a set of types is also a set of trees, also called a tree language or a forest. Tree languages are formally defined using tree grammars. Tree grammars generalize word grammars like regular expressions and LR grammars for trees. The productions of a tree grammars are tree rewrite rules, where the left-hand side is a variable node and the right-hand side is a tree form with which the variable can be substituted. Like in the string case, the classes of tree grammars, like regular and context-free tree grammars, are defined by certain restrictions to the form of productions. Enter subtyping machines. A subtyping machine is a program that uses subtyping to recognize a tree language. A program contains a class table, which is a set of inheritance rules, followed by a subtyping query that needs to be resolved against the class table. The subtyping machine comprises the class table and the left-hand side of the subtyping query. The input to the subtyping machine is a tree. We take this tree, encode it in a type, and put this type on the right-hand side of the subtyping query. The machine runs by resolving the query. If the query is true, then we say that the machine accepted its input. And if the query is false, then the machine rejected the input. The tree language recognized by a subtyping machine contains all the trees which it accepts. In the paper, I investigated the computational power of subtyping machines in the decidable type system fragments of Canadian peers. The first fragment forbids expansively recursive inheritance. Informally, expansive inheritance allows the expansion of types through inheritance to be unlimited. For example, let's say that class A of X inherits from B of A of B of X. Then we can take the type AC and use inheritance to get the type BA, BC. Then we decompose this type into ABC by removing the outer B. Then we use inheritance and decomposition again to get ABBC, and so on. So we can start with type AC and get the type ABC with a sequence of B's of any length. Therefore, the original inheritance rules is said to be expansively recursive. My first result is that subtyping machines whose class tables are not expansively recursive recognize regular tree languages. In other words, we can take the productions of a regular tree grammar and encode them as a subtyping machine that recognizes the same language as the original grammar. Let's see the example from the paper. This example is for the tree language of cons lists of piano numbers. So a piano number is either a Z or an S of a natural number. And a list is either a nil, the end of the list, or a cons of a natural number and a list. To encode this grammar in a subtyping machine, we first encode the grammar terminals. Notice that we use covariance in the type parameters. Next, we encode the grammar productions. Each production is directly encoded as an inheritance rule. For example, a natural number is derived to Z or S of natural number, and therefore interface NAT inherits from Z and from S of natural number. Finally, we can run the subtyping machine by writing down a variable assignment. The variable type of this assignment is a properly encoded cons list of piano numbers, so therefore the assignment compiles correctly. To complete the proof, we also need to show the other direction, that every subtyping machine without expansively recursive inheritance recognizes a regular tree language. This proof is a bit more complicated, but you can find it in the paper. The second fragment forbids contravariance. I found out that subtyping machines whose class table do not use contravariance recognize context-free tree languages. But these languages must have grammars in Greibach normal form. Like before, we can take the productions of the Greibach normal form and encode them in a subtyping machine. For example, the language of palindromes is a non-context-free language that has a grammar in Greibach normal form. We can encode this grammar in a subtyping machine. Following the subtyping machine, there are two variable assignments. The first assignment succeeds because the variable type encodes a palindrome, but the second assignment does not compile because the variable type is not a palindrome. Like before, you can find the other direction of the proof in the paper. Besides the theoretical contributions, I also investigated the metaprogramming potential of subtyping machines. Apparently, some APIs have context-free usage protocols. For example, the Android Canvas API states that it is an error to call restore more times than save was called. We can formally specify this protocol using context-free productions, as seen on the bottom of the slide. For example, we can draw on the canvas by calling draw. Then we can save the picture, draw again, restore the saved picture, and restore again. But then the Canvas application throws a runtime exception because we called restore twice on a single save. We want to use subtyping machines to recognize these kind of problems earlier at compile time. In the paper, I described Treetop. Treetop is a subtyping machine compiler. The input of Treetop is a context-free grammar that describes an API protocol. The output of Treetop is a C# fluent API that enforces this protocol at compile time. It uses a subtyping machine. For example, we can use Treetop to generate a fluent API for the Canvas API, for the Canvas application. And then we can invoke this API using a chain of method calls in a fluent style. However, in this case, the fluent chain fails at compile time. That is because the last method on the chain invokes a subtyping query. This subtyping query depends on the methods called earlier on the chain, and it runs on a subtyping machine generated by Treetop. In conclusion, we showed a correspondence between nominal subtyping and tree languages. This correspondence was established using a mechanism called the subtyping machine that formalizes computations of subtyping. We also discussed metaprogramming applications of subtyping machines. There may not be many opportunities to use subtyping machines in a real program, but still, we showed that context-free languages can be recognized at compile time in a decidable type system fragment, which is a nice contribution to the academic study of fluent APIs. Thank you.